What specific problem does your method aim to solve regarding transformer interpretability? And how does this relate to the limitations of existing methods like probing and sparse autoencoders?
Our method aims to address the limitations of existing transformer interpretability techniques, such as probing and sparse autoencoders, which primarily focus on extracting interpretable signals from model activations. These methods often overlook significant aspects of the computation, potentially missing critical features that contribute to the model's decision-making process. In contrast, we investigate the concept of native information content, which provides a more holistic understanding of how transformers encode and generalize information, particularly in tasks like two-hop question answering. By measuring how information content scales with model size, we can gain insights into the model's generalization capabilities, which probing methods fail to capture comprehensively. This approach allows us to explore the relationship between information compression and learning, offering a new perspective on transformer interpretability that complements traditional methods.
How does the proposed method for assessing the native information content of transformers operate? Please illustrate the step-by-step process of your methodology, including any equations or models introduced in the context of two-hop question answering.
The proposed method for assessing the native information content of transformers involves measuring the information content scaling of transformers trained on two-hop question answering tasks. First, we define the dataset entropy, which quantifies the uncertainty in the dataset based on the number of profiles and their attributes. For instance, the entropy for one-hop questions is calculated as h equals n log underscore 2 n underscore 0 plus sum underscore a in a log underscore 2 v underscore a, where n is the number of profiles, n underscore 0 is the total possible name combinations, and v underscore a represents the set of possible answers for each attribute. Next, we compute the effective loss for the model, which is the difference between the dataset entropy and the sum of cross-entropy losses over all answers. For two-hop questions, we consider different computational models: the recurrent model, where the dataset entropy is the same as one hop, and the two-function model, where first and second hop relations are treated as independent facts. The information content is then derived from these losses using the equation I equals HL, where I is the information content, H is the dataset entropy, and L is the loss. This methodology allows us to assess how well transformers can generalize and utilize their learned information in answering complex queries.
Can you provide a concrete example of a two-hop question and demonstrate how your algorithm processes it? Walk through each computational step your algorithm takes to arrive at the answer.
A concrete example of a two-hop question is who is Bob's mother's boss? In processing this question, the algorithm first identifies the components: E_1 Bob, R mother, E_2 Bob's mother, A boss, and S the answer. The algorithm utilizes a function f that memorizes relationships, allowing it to compute the first hop by evaluating f Bob mother to retrieve Bob's mother. Next, it applies the same function again to compute the second hop by evaluating f Bob's mother boss, which yields the final answer. This two-hop process illustrates the necessity of reusing the function f across different layers, as the transformer architecture is feed-forward and cannot revisit previous computations, thus requiring the model to learn separate functions f_1 and f_2 for each hop.
According to your findings, what are the key theoretical or practical advantages of using the two-function composition algorithm over previous models? How do these benefits manifest in terms of generalization and performance?
The two-function composition algorithm demonstrates key advantages over previous models, particularly in its ability to generalize effectively to unseen two-hop questions. Unlike the hash table model, which only answers questions present in the training data, the two-function composition allows for the reuse of learned relationships, enabling the model to answer new questions as long as the relevant components are present in the training data. This is evidenced by our findings that models employing this algorithm could generalize to held-out entity-attribute pairs, while those relying on independent memorization failed to generalize at all. Additionally, the two-function composition algorithm aligns better with the observed information content scaling of transformers, suggesting a more efficient use of the model's capacity. Overall, these benefits manifest in improved performance on two-hop question-answering tasks, as the model can leverage learned functions to navigate complex relationships rather than relying solely on memorization.
What validation techniques did you employ to assess the effectiveness of your method, including the datasets used and the metrics for evaluating performance on two-hop questions?
To validate the effectiveness of our method for two-hop question answering, we generated synthetic datasets of fictional profiles, varying the number of profiles from 1,000 to 250,000, and created held-out sets of two-hop questions by systematically excluding specific components, e.g., first entities, first relations, from the training data. We employed a training regime where each model was trained on a ratio of 1-hop to 2-hop questions, specifically one 1-hop question for every 10 2-hop questions, to ensure that the models learned to generalize rather than memorize answers independently. Performance was evaluated based on the model's ability to generalize to unseen questions, with metrics including the accuracy of answers to held-out questions and the comparison of information content scaling against the expected capacity of 2 bits per parameter. Additionally, we conducted empirical assessments of generalization by analyzing the model's responses to various held-out components, which provided insights into their learning mechanisms and the effectiveness of the two-function composition algorithm. Overall, these validation techniques allowed us to systematically assess the model's generalization capabilities and the underlying algorithms they employed for two-hop reasoning.
What specific results did you achieve with your proposed approach, and how do these results compare with existing capacities or performance benchmarks in similar tasks?
In our study, we trained transformers on synthetic two-hop question-answering QA datasets and found that the two-function composition algorithm provided a qualitatively better fit to the assumptions about knowledge capacity and dataset entropy compared to other models. Specifically, we observed an information capacity of approximately 1.6 bits per parameter for 1-hop QA, which is lower than the previously reported 2 bits per parameter. For 2-hop QA, the scaling of information content suggested that transformers exhibit a stacked curve behavior, beginning below the hypothesized capacity and approaching it as dataset entropy increases. Additionally, we found that 2-hop QA datasets required about 10 times longer to learn than 1-hop datasets of similar size, indicating a significant challenge in learning complex structured data. Overall, our results suggest that while transformers can achieve substantial performance, they face limitations in generalization and efficiency compared to existing benchmarks.